In this video, I'll be explaining the full process of how to laminate and vacuum bag a complex hollow carbon fibre part like this drone fuselage, including, in a YouTube first, showing how to make and use silicone intensifiers to improve consolidation in difficult areas. I will then go on to bond in the longerons, bulkheads and spars to create the finished part that you see here. I'm Paul from Easy Composites. In recent videos, I've been using the example of this drone fuselage to explain how to make multi-part moulds. And that is where I was going to leave it. But from the comments on those videos, you clearly wanted to see how the part itself was done. So let's get into it. This is the component we're making. It's the fuselage for a flying wing drone, and it includes all of the internal structure that provides strength and mounting positions for the hardware, and it also has the spar tubes that will accept the wings. This definitely isn't going to be the simplest part to make, but who doesn't like a challenge? The starting point for anything like this will be the moulds, and in the case of a hollow part, you will need a mould that will split into 2 or more pieces. In this case, we actually have a 4-piece mould, so we've got the main upper and lower sections of the mould, then we've also got some side plates that form the wing roots. The moulds themselves are made from XT135 tooling prepreg and also include metal mould clamping bushes that allow the parts to align and be clamped together. If you're interested in getting more details on exactly how these are done, then we've covered both the design and manufacture of these in previous videos linked below. So that's the moulds. What about the part? Well, there are a few ways you could approach making this, including a simple wet layup, but I want to use lap joins to connect the 2 halves together and then cure this part in one piece under vacuum. And so the most practical approach is definitely going to be to use prepreg carbon fibre, where I'm going to get very accurate control of the ply placement. But vacuum bagging and curing this in one piece could be problematic. If we look at how these moulds come together, we're left with a very sharp, fine detail that forms the trailing edge here. And if you imagine trying to vacuum bag down into here, it's going to be very difficult, if not impossible, to get that bag to conform without bridging. And if you have bridging, you're going to have a lack of consolidation, and that's going to lead to pinholes on your part. Fortunately though, there is a solution, and it's these. These are silicone intensifiers. So they're a rubber insert that get installed into these complicated areas and allow consolidation into those detailed bits where the bag wouldn't normally follow. In its uncured state, it's a very soft and pliable material, not that dissimilar to a modelling clay, and it's used by pressing down into any of those complex and detailed areas. Then it's cured under heat, and that forms these flexible rubber inserts that can be reused indefinitely. Although it's the accepted term, I think that the name intensifier might be just a little misleading, as it doesn't really intensify the pressure. Instead, it really just fills the gaps where bridging would normally occur and then allows the vacuum or autoclave pressure to do its normal job in these areas. Either way, they can be extremely useful in those intricate details and are going to typically make the vacuum bagging operation less challenging and therefore faster. The most common way to make your silicone intensifiers is to do your layup as normal, put your release film down, and then press the intensifier material into any of the complicated areas. This is then cured under a vacuum bag in the normal way, and your silicone will cure alongside the prepreg, and after demoulding, you'll be left with your part and your reusable silicone inserts. But for this wing root area, I'm actually going to be taking a slightly less common strategy and make my inserts directly against the mould surface. Now this is only possible if you've got a very thin laminate of 1 millimeter or less, as it doesn't account for any of the material offset that you get. Instead, it relies on sort of squashing and compressing that silicone out of the way. If you are planning to make your silicone intensifiers like this directly against the mould surface, it's really important to separate it using a release film, as this silicone will grip onto the mould surface, which is going to make separating it very, very difficult in the end. And I found this out the hard way. So to get started, I'm now going to lay down some release film and press the material into the rough shape. When doing this, try to ensure that you don't leave voids in the silicone. You want to load in an amount that's going to be sufficient to fill in all of the details where you think that bridging of the vacuum bag could occur. It's not an exact science, but being so pliable, it's really easy to add and remove material as required. I'm using our Intensil 40 product, which is a 40 Shore intensifier compound with excellent pliability in its uncured state, and really easy handling with an outlife of 6 months at room temperature, or considerably longer if you store it frozen alongside your prepregs. To get these finished, I will now close the mould and press and blend the silicone into the mould surface. You're looking for a fillet or a feather edge here. If you were to leave a sharp transition, this may cause vacuum bag bridging in its own right, leading to a print through on the surface of the part. It's probably a bit difficult to see, but I now have all of the difficult to access areas filled with a smooth transition. The next step is to vacuum bag this to ensure full consolidation. Although not absolutely necessary, vacuum bagging the intensifier will help to reduce any voids in it and also smoothens and blends the surface further. Ensure that all of the silicone is covered in release film, then wrap this with breather fabric and vacuum bag in the conventional way. Check the Intensil datasheet for alternative cure cycles, but here I'm curing under full vacuum for 1 hour at 120 degrees C. Once cooled, the vacuum bag and breather are removed. The mould is separated and the release film peeled from the pieces. After curing, we now have our silicone intensifiers. Being a 40 Shore A hardness, they are very flexible, and that's really helpful as it allows them to conform that little bit under the vacuum and properly consolidate the laminate underneath. They also very accurately follow all of the sharp shapes and contours of the mould, meaning that our bag won't have to go into those areas in the final cure. And being incredibly strong, these things are going to last indefinitely. I'll be using XC110 Prepreg carbon fibre for this, which needs to thaw before being removed from its sealed bag. While the prepreg defrosts, we can now get on and create our templates. There are a few ways you could tackle this. You could flatten out the surfaces from a CAD model, but I'm going to take the old school approach and use some masking tape. The tape is applied over the entire surface of the mould, and then the cut positions are marked onto it. The masking tape is then carefully transferred to a flat backing material to create the cutting templates. Now let's talk about the lap joints. I'm going to be laminating this part in 2 separate halves and then bringing these halves together and vacuum bagging them and curing them into one monolithic structure. But if I was to just laminate each half of this with my 2 plies and finish at the parting line, I would have a very weak structure as the skins would be effectively just butt joined with no fibre reinforcement crossing over that seam. A simple way to approach this would be to shorten the inner plies slightly and then apply a tape on the inside to link them together. And this is often the way it's done, but it does have one major drawback: access. Very often it's just not possible to reach in and apply that tape down accurately. Even on a part like this, it would be very difficult. But imagine on the bike frame that we did in a previous video, it would be almost impossible. So instead, we're going to extend one side beyond the parting line, pull back the other side, and then we have a lap join. And that means we can close the mould and the vacuum bag will press that lap onto the other one, and we know exactly where it's going to be. Using this method, we could also add an additional seam ply if extra strength was required, but for this part, it's not going to be necessary. Now that the prepreg is fully defrosted, I can start cutting out the kit of materials. And since I know the lap strategy, I can extend or shrink the templates to give us the extension or pullback on the reinforcement that we need. I'm also taking my silicone intensifiers and templating around them too. I can now get on with cutting the carbon fibre prepreg, which is really easily cut to these templates using a scalpel or scissors. You can find out more about the very special Xpreg XC110 Prepreg system on the Easy Composites website, where you will also find all of the products and materials used in this video series, including the tooling board and tooling prepreg used to make the mould, silicone intensifier compound, vacuum bagging consumables, pump, and even the curing oven, which are all available for delivery to most countries worldwide. So that's everything set ready to get started into the layup. Before I do though, I'm just going to give these a quick top up with release agent. A coat of Easy-Lease CR1 is applied to all of the mould faces with a lint-free wipe, allowed to cure, and then the prepreg is laminated down. As discussed, the lap strategy will see the surface plies trimmed perfectly to size and come together to form a neat butt joint at the parting line, with the second ply shortened on the lower half and then extended on the upper half. This creates the overlap that will join the halves together. So the first ply of the lower surface is laminated and then carefully trimmed back with a scalpel to meet the parting line. When you're doing this, be really careful to present a flat blade surface as to not scratch it, as otherwise you will find that your mould might not last for that many cycles. As with any layup, great care is taken to ensure that the material is pressed down into all of the details and follows the mould's contours and surfaces as closely as possible. Now onto the upper surface, the first ply is laminated and trimmed back to the parting line in the same way as we did on the lower one. Back onto the lower surface, the second ply is now added. This time it stops 10 mm short of the parting line. Finally, we're back onto the upper surface and the second ply is now added, which extends an additional 10 mm beyond the edge, creating the lap that's going to join these two halves. The wing roots have separate pieces that are tailored in to fit the form. I've now got the two sides laminated up. So on the upper side, we have our extension that runs all the way around, and this is going to create that lap to connect to the lower side. I've also got these additional pieces in at the wing roots, and these are then going to wrap over our silicone intensifiers to join the two halves together. Then on the lower side, we have the first ply cut exactly on the parting line of the component, and then the second ply is staggered in from this, and that allows the lap from the upper one to butt join up to it. So let's now take a look at getting the intensifiers into here and getting the moulds closed. First, I'm attaching my barriers and making sure that the prepreg is properly pushed up against them. Before positioning the intensifiers, release film needs to be applied. This allows the inserts to be easily removed later and also prevents any silicone contamination affecting the part. Once in place, the lap of carbon fibre can be then carefully folded over the intensifier, ensuring that it will be correctly positioned when we close the mould. The rest of the laps are then folded into approximate position, and you can now see quite clearly how these laps are going to work to connect the pieces. A neat little trick to holding the laps in position is to use some flash release tape across the mould to keep them folded down. This reduces the risk of the carbon fibre folding the wrong way during closure and becoming trapped in the flange. When the moulds are initially closed, the tape can then be pulled out, leaving the laps in the right place. After clamping down, the prepreg is then completely covered in unperforated release film and secured in place with flash release tape. With the release film down, I'm now going to take the opportunity to show you how you would normally use this intensifier material. Earlier, we made the intensifiers directly against the tool surface. Now this is only possible to do if you're going to have a very thin laminate of 1 mm or less. Normally, you would do it at this stage. So after you've done your layup, put your release film down, You would then go around and press your intensifier into any sharp corners or details that you want to smoothen out. The area that I'm going to demonstrate this on is in between the grip launch in the bottom of the fuselage. Now, this isn't a particularly detailed area, so it doesn't really warrant having an intensifier, but I thought it's going to be a good opportunity to show you how you would normally use it. The material is worked into the surface in just the same way as we did for the wings. Again, blending it into the part surface to ensure that we don't get a sharp transition that could lead to print through. This is then covered in a layer of release film to prevent it from sticking to the vacuum bag, and now the entire part can be wrapped in breather, vacuum bagged, ready for cure. Bagging hollow parts requires a vacuum bag that is sufficiently large to allow it to reverse in on itself inside the mould. As always, great care must be taken to ensure that the bag is following all of the contours without bridging or stretching. Although this is definitely made much simpler with the intensifiers taking care of all of the really difficult spots. Once bagged, the part is loaded into the oven and cured using the standard XC110 cure cycle under full vacuum. Now we're on to my favourite part of any composite project, the demould. As soon as the side plates are removed, I can already see that the intensifiers have done a great job, leaving crisp, void-free corners. The part then pops out with no problems, and I can remove my silicone intensifiers. This fuselage is already looking great. I can now remove the flash and get the edges trimmed back with a permagrip wheel and sanding block. Then it's a bit more permagrip action to trim the holes for the spar tubes. With the main fuselage component complete, we can now move on to the internal structure. So we've got the floors, the ribs, the bulkheads and the spar tubes. And to achieve the maximum stiffness for the minimum possible weight, these parts have been made from a lightweight carbon fibre sandwich panel, and this is very common in UAV construction. The panel was made using a single ply of 210 gram Prepreg carbon fibre, either side of a sheet of 3mm rower cell PMI foam. This was then vacuum bagged against a sheet of glass and oven cured following the standard XC110 cure cycle. The profiles were then cut from the material on a 3-axis CNC, which, as you can see, results in these incredibly light yet surprisingly stiff components. The motor mount, which carries a lot of the load from the motor and also has bolts running through it, has been machined from some stock solid 2mm sheet, which is manufactured by us right here in the UK. The next step is to get this internal structure bonded into the fuselage. Now, as you'd imagine, the strength of these bonds is going to be quite critical to the performance and reliability of this aircraft, and so getting the right adhesive will be very important. When it comes to bonding composites, there are really two main chemistries that you might consider. There are methyl methacrylates, known as MMAs, or structural epoxies. Very often, an MMA such as our VM100 will be a great choice, as it does have an excellent balance of price and performance. They cure quickly and bond to a really wide range of materials. And while they don't have the out-and-out performance of an epoxy, generally they will still outperform the substrate. So it's going to be the carbon fibre that tears apart before the adhesive fails. So having a higher performance is pretty much meaningless. But for this application, where we've got really critical edge bonds of these components into the fuselage, we really want the highest possible performance from our adhesive. And so we're going to be using the Permabond ET5428. Now this one has a working time of around 10 minutes, which is great for small assemblies like this, but we do also stock a 2.9 version, which gives you up to 2 hours of assembly time on your structures, allowing you to make very, very large and complex assemblies. The first stage of any adhesive application is to prepare your surfaces. So let's get started with that. The parts are positioned and their locations scribed on, so I know where to key. Preparation for bonding with ET5428 is the same as for most other adhesives, so that's a case of keying the surfaces to be bonded with abrasive paper. Peel-ply surfaces wouldn't need keying, but these being straight from the release film, they will do. I'm using a fairly fine 240 grit abrasive on these very thin materials, as it's important not to sand too far into them. Then just blow or wipe away the dust and degrease thoroughly using an IPA wipe. For bond preparation, 100% IPA is recommended as it's more powerful degreaser and won't leave any residual moisture, particularly on porous substrates. Using a dispenser gun with a static mixer nozzle, the adhesive can now be applied. I like to sacrifice a small amount of the adhesive at the start, as there's always a bit of a chance that it's not perfectly mixed. It's then applied in a thin bead along each of the bonding faces. ET5428 has a working time of around 10 minutes, which is more than enough for this job, but as I mentioned earlier, we do have the 2.9 version that will give you over 2 hours if you have a complex assembly to bond. This adhesive is quite thixotropic and stays nicely in place on these edges prior to the final positioning, allowing me to apply a sufficient bead to gap fill the slight texture from the bagging process on the inside of the fuselage. Wherever possible, I try to create a small fillet, as this helps to increase the contact area of the adhesive and reduces any stress concentrations. A quick run over with a lollipop stick can be really useful for this. The spar tube then receives a good bead and any excess is wiped away. With the adhesive cured, I'm now going to key the surface with 400 grit abrasive ready for paint. Typically a UAV would be painted in a solid colour, but I want to keep the carbon visible, so I'm going for a satin clear. The Phantom Clear paint I'm using here is designed specifically for carbon fibre and goes down incredibly well. High quality satin or matte finishes are slightly quicker to achieve than full gloss ones, generally requiring just a single coat, flat, then a finishing coat. Doing this did add around 10 grams to the part, but for the protection and looks, I think it's worth it. I think that the finished fuselage looks absolutely awesome in satin, and it weighs only a few hundred grams. Well, it would do if it didn't have the motor in the back here. Just looking at it and holding it really reminds me of what Composites is all about, why it's so difficult, and why I love it so much. Although on the face of it, it might not look that complicated, when you think back at all of the work, processes and materials that it's taken to get to this point, from the CAD design to machining the patterns, then laminating and curing the molds, and then everything we've done in this video with intensifiers and adhesives, I really can't think of another engineering discipline that encompasses so many skills, techniques and materials, or one that can be as challenging and sometimes frustrating as composites can be. But if you're anything like me, then this is what keeps it so interesting and so rewarding. If you'd like to learn more about some of the processes that we've only managed to skim over in this video, then I'll put a list of links in the description to some other videos that will cover them in more detail. Or maybe check out this video to go back to the beginning and see how the tooling for this drone was done. And of course, if you're looking for the very best in composite materials and equipment, then visit the Easy Composites website or get in touch with our technical sales team today. Thanks for watching, and I'll see you next time.